Okay. Can you hear me? Can you guys hear me? Give it a thumbs up. I'm in a new setup, so I'm not sure. Is everything audible?
Yes, sir.
Okay. Now, hmm, I'm going to start off with the last class. Actually, we looked into capacitance, almost finished it. We talked about these equations. We shared how to find the energy stored in a capacitor. We found out multiple ways to do that. We found out how half QV is relevant. That is, as charge increases, voltage across the capacitor also increases. So it's not that right from the get-go, you have a certain amount of voltage applied, so every charge going in will face the same work done. No. So as charge increases, voltage also increases. So that happens in proportion. Hence, we take the line area under the curve. And that area under the curve happens to be half QV. That is the energy stored in a capacitor. Granted, that's the case. I also go ahead and substitute other variables in from other equations. And what I find out is energy can be expressed as half CV squared. It can also be expressed as half Q square C by C. And these are the three main ways that we can have or find out the energy stored in any capacitor. Okay, granted, I know it's capacitance. Granted, I know it's voltage applied. That is the final voltage across it. Now, today, what do we do? The main part of this conversation or today's class, not the only main part, but we are also going to traverse into magnetic fields. Regardless, one of the main parts is going to be capacitor discharge equation. I'll show you guys in bits how basically the derivation works, how this equation is derived of discharge. So we want to be able to understand how the energy of a capacitor is discharged with respect to time, because the discharge for a capacitor is very important, because that is a very important factor that determines its application in multiple circuits. So how a capacitor discharges is very important as an attribute for the capacitor being used. And it is less about the capacitor itself and more about the setup of the capacitor that determines how the discharge takes place. Now, before I start, which is with the topic that is exactly in your syllabus, I need to clarify a few things so that you don't get things wrong in your exam paper. Okay. And this is I have sat down and found out like 4 or 5 things which students usually tend to get wrong or have a misconception about. Okay. So I'll start off one by one from these. I'm audible, right? As in, I'm not lagging. My internet is pretty bad over here. I'm audible. Give a thumbs up or just tell me everything's good. It's not lagging. It's lagging. Is it lagging? Can you hear? Okay, I'm gonna assume it is not lagging. because someone said it's not lagging. And I'm going to move on thinking it is not lagging, okay? So if it is lagging, just let me know if you can hear me. If you can't hear me, then, well, I don't really know. Anyways, so basically, I'm breaking the concept misconceptions out in 5 parts, or 5 parts. And the first thing that I want to talk about with you guys, it is lagging, isn't it? Can everyone hear me? Is it all right? In worst case scenario, recordings will be there. So I'm gonna move on. Okay. So first thing that I want to talk about with you guys is how the potential difference for a resistor can be gauged in a series circuit. Okay. So the misconception mainly is about over here is, let's say I draw a circuit for you guys. Okay. So this is a resistor, and then I have a capacitor. Something like this. But this is a capacitor, this is a resistor, and this is my supply of EMF voltage. Okay, fair enough. Now, what I want to talk about over here is how or what do we find out as a voltage when I have a voltmeter measuring the voltage across the resistor. What do we find? Now, first class, when we started discussing about capacitors, how it is in a circuit, we said, I said, by having the conversation that, well, the resistor will have some amount of shared potential difference, which is true, but not entirely. True how? Basically, when it is charging up, when the capacitor is charging up, the resistor will indeed have some amount of potential difference across. So you do see a reading over here on this resistor. When charging up, the resistor has a PD across it. Okay. But when it is completely charged, okay. So when completely charged, there is no potential difference across the resistor. Why is that the case? For one thing, think of it logically. That let's say I have the electrons flowing in this direction and in this direction, and this becomes again the negative pole, and not the pole, but negative plate, and this becomes a positive plate. So notice once you have such an accumulation of charge over here and it has its own stored energy, it acts as a source of energy as well with the same PD or same voltage as my supply voltage. So let's say my supply voltage is 12 volt, and after getting completely charged up, the voltage across the capacitor is 12 volt as well. So what happens in this case is, if this is the positive plate, and if I take the conventional current route, current through this cancels the current through this, technically speaking. So after a point, what really happens is over here, right now, there's no movement of charge. Okay. So across this resistor, there is no potential difference really. It's zero. So if you attach a voltmeter over here across the resistor, what will you see? A zero potential difference in this voltmeter. Granted, you have completely charged up the capacitor. Okay. Now, what happens if I have a light added over here? What happens if I have a light added over here like this? What do you think? After a point when the capacitor is completely charged, the light will also not light up. So this, granted it has a zero potential difference across it, that is due to the fact that this being completely charged up allows no charge to flow in the entire circuit anymore, because it is, if this is the positive pole, this is positive pole. If this is negative, this is negative. So no current is flowing over here. So hence I have a circuit where the bulb no longer lights up. So in this process, what really happened is initially, when the capacitor gets charged up, light does light. It does glow. As time proceeds and the capacitor keeps getting charged, it basically gets dimmer. So it loses the flow of current through it, right? The rate of flow of electrons decreases. Hence, the light will get dimmer and eventually it turns off. Now, I did mention to you guys something last class probably, or before that, that the light will continue glowing in such a circuit. Now, my bad or my mistake was what I didn't clarify is, in that case, that would have to be an AC supply, not a DC supply. What does a direct current mean? A direct current supply means it is current in one direction. Hence, if charge is flowing in this direction, that is electrons flow in that direction, that is the only route through which electrons can flow. That is, it is DC supply. In case of DC supply, direct current. So once it is charged up, it doesn't discharge. Granted, I have the DC supply connected. So I supply 12 volt and it matches, or the capacitor gets charged up and it also has 12 volt. No longer will current flow because both of the voltages are put in such that they oppose current flow, because conventional current over here flows this way and over here flows this way, it wants to flow that way. So hence, no current is flowing. Lump sum. Now, what happens if I have AC current? Alternating current. Things are a bit different because it's in the name that it's alternating current. Hence, for half a cycle, I have electrons flowing in this direction. For rest of the half cycle, I have electrons flowing in this direction. Okay. So real current, talking about real current, electrons can flow in this direction or in this direction, both. Half cycle, half cycle, half cycle, half cycle, it keeps alternating. And what happens in that case is the capacitor goes through a process of charge and discharge constantly. So in such a case, the light glows constantly, even though there's a capacitor in series. Okay. Now, since the capacitor in series and bulb is also in series, and I have a AC supply, what really happens is electrons keep flowing through the circuit. Half a cycle in this direction, half a cycle in the other. So since current flow remains in the circuit, the bulb does continue glowing. What really happens is that it can be that your bulbs, I mean, what do you at? Intensity may vary as the cycles proceed, but it's not going to affect much. And you will see why when I teach you guys AC current chapter and how, the capacitor really affects the circuit. So you will see how AC current is the what do you call it? The graph will look like when AC current, sorry, when a capacitor is included in. So you'll get to see how the cycles vary like this. Okay. So it charges, discharges, charges, discharges, and you'll see how this really works. So ultimately, in case of an AC current, the bulb continues to glow up even though it is in series with a capacitor. Not a problem because current continues flowing. Okay. So that is one of the common misconceptions that people have. And I tried to clarify that. What happens when you have DC current and other components in series, and what happens when you have AC current. Okay. Now, the other thing I will show you guys, these are two things I've mentioned. One is AC current situation, DC current situation, and in series. The other thing I want to mention to you guys is, what is this? Okay, so let's say I have a power supply, let's consider DC current supply, direct current, and now I have a capacitor and I have a bulb. Okay, I have a bulb, and let's say this is 12 volt of supply, and this is some capacitor. This is bulb. Can anyone tell me? Granted, this is fully charged. Fully charged. Can anyone tell me if the bulb continues glowing or not after the capacitor is fully charged? Take a guess. Do you think the bulb glows after the capacitor is fully charged in this setup when it's parallel? Yes or no? It glows or not? Okay. Okay. So yeah, in this case, what we have is the bulb does glow. Why is that? So what really is happening over here is, remember, in parallel circuit, potential difference across these 2 points, same as 12 volt. Potential difference across these 2 points, same as 12 volt. Now, when this is fully charged, what happens is the current or the electron flow will avoid this path. Because of course, if this is positive plate or of the cell, and this is also a positive plate of the cell, and this is negative, and this is also negative plate of the cell, the current can't really flow through it. Okay. So what really happens is it goes through this latter um, circuit path, let's say, and the bulb continues glowing because what? That is the easier path to traverse for the electron. Okay. So that is why the bulb will continue glowing with 12 volt across. Fair? So the bulb in a parallel circuit does glow. Granted, you have a DC supply, let's say. I mean, even AC supply it will glow. But anyways, you have a DC supply and the bulb will glow. Granted, it's in a parallel setup with the capacitor. Okay. It doesn't matter if the capacitor is charged or not charged. What is the next thing? Let's see. So yeah, a lump sum, this is all the common misconception I want to cover. Yeah, I covered two things here and one other thing over here. And you may have some confusion here. If you do, let me know in the classroom. I'm pretty sure most of you guys can't even hear me right now. But anyways, if you do have confusion when you're watching this recording, let me know in the classroom. Okay. So these are the few things I want to get over. Is there anything else now we can talk about? No. So the thing I'm going to cover today is how the discharge for a capacitor looks like. How does discharge happen for a capacitor? Okay, so it gets charged up. I get that, and in a typical series DC circuit, the capacitor gets charged up, and eventually, it will discharge. Now, I understand the charging process. How? We've looked at these these three graphs, how the charge accumulation on the plate of a capacitor looks like, how the current through the plate looks like, and how current in the circuit looks like, and how the voltage across the plates look like. So this is the charging process. Let's look at this, similar variables, but in the discharge process. Let's look at that. Okay. So what happens when the discharge takes place? Quite intuitively, what we have is a few of these things: voltage, current, and charge. And you can qualitatively understand what's happening here. Let's start with the first one. What happens to the voltage across the capacitor? So let's say this is a setup I have, right? This is a setup I have. And when connected to C, it is a typical CD circuit with a power supply here, a resistor here, ammeter measuring current, and the capacitor being charged and discharged. So when it's connected to C, the capacitor gets charged up. And after a point, when it's completely charged, current stops flowing, even though it is connected to C over here. Okay, so current stops flowing in that case, and we have a fully charged capacitor. Good. Now let's do something else. Let's connect this switch to D, and you know what will happen? This thing acts as a circuit over here. And the capacitor will discharge. It will release the stored energy in itself. Okay. So as it does that, how does the energy curve look like? How does the current in the circuit look like? And how does the charge accumulation in the plate look like with respect to time? Initially, let's start off with the voltage. What is the voltage across this? So in the discharge process that is connected to D, 12 volt. Let's say supply was 12 volt. And initially in the discharge process, I have 12 volt across the capacitor. So voltage initially maximum 12 volt. Good. Right? And this part should be connected to the y-axis. Always remember that. Why? Because it is a known value. It is not going to be an asymptote over here. Nope. It is a known value. It is at time is equals to 0. It is not infinity. It is 12 volt. So this part of the curve should always meet the y-axis. Always remember that. Discharge takes place. And it looks like a typical, right? Y is equals to e to the power minus x curve. Similar to it. Okay. Now, why does it look like this? You will ask. Well, initially, potential difference is maximum, or the power supply, call it, or the voltage initially is maximum 12 volt. So a lot of charge initially gets to flow through the circuit and gets discharged as it loses energy through the resistor. And with time, as charge leaves the capacitor, less charge is left. So initially you have 10 charge left, right? At the next cohort, 8 charges will leave. Why? Because the charge concentration over here on the plates decrease with respect to time. What did they do? They decrease with respect to time. Since the potential difference is less, as the charge accumulation decreases on the plate with respect to time, less and less charge travels through the circuit because the density of charge on the plate has decreased. It is a similar logic we applied when the charging conversation was taking place of a capacitor. So the discharge is also a typical e to the power minus x curve. So it decreases with decreasing gradient. Right? So the charge keeps decreasing as time proceeds, and in this manner. Okay. We will see why it looks like this, and we will find out the equation for it, for the discharge, and it is, of course, e to the power minus something. All of these, voltage, current, and charge, all of these will be found out as e to the power something minus something. And you'll see this later on when we derive it. Okay. So the voltage decreases in that manner. Similarly, current also decreases in a similar manner. Why? Initially, like we use a typical V is equals to IR, nothing else, as resistance stay constant, right? Resistance is what? The resistance of this resistor. It is a constant, right? And how does the current vary through the circuit? As voltage decreases, current also decreases. Simple proportionality. Got it? So if this is how it's shaped, similar shape will also be seen with the current graph. Nothing else. Got it? So it's simply the formula acting over here. And it's also logic. Charge accumulation decreases or charge density at the plate decreases. So rate of flow of electrons with respect to time decreases. Simple. Okay. Next thing is charge accumulation on the plate, right? Initially it's maximum, and with respect to time it decreases. Why? Because charge is flowing out. Initially, large accumulation of charge, they rush out much faster. When it's less, there's a less force or electromotive force, and less amount of charge will be flowing out through the capacitor. So as the concentration decreases of charge on the plate, less amounts of charge will be traveling out. Okay. So with respect to time, the charge, amount of charge on the plate decreases with decreasing gradient. Initially, let's say it's a steep decrease of charge, 10 charge or 10 electrons move out. Then it's 8. Then it's, let's say, 9. Not 9. Let's say it's 7. Then it's 6. Then let's say it's 5.5. So on and so forth. So the charges keep coming out of the plate with decreasing amounts. That's what the decreasing gradient represents. Okay, got it? So what is happening over here? We have looked at three variables. Three different functions over here. Charge versus time, voltage versus time, current versus time. Okay, and all of these, what we found out is it is typical y is equals to e to the power minus x curve. All of them with decreasing gradient as time proceeds. And you will find out the formula for it. Okay. So this is how the discharge happens of capacitor. Very important. Very, very important. Okay. Now comes the real part. How do we derive the discharge equation? What do I mean by discharge equation? What I mean to say is I want to find out from time is 0, where capacitor is fully charged, to time n, let's say, any amount of time after 0. It's a 1 second, 2 second, 3 second, 300 second. At that specific second, granted the capacitor is discharging, I want to find the exact voltage of it, exact potential, charge on the plate, and exact current in the circuit. What I mean by that is if I have a fully charged capacitor and I connect it to D now, which means it will start discharging. So at time 0, the voltage is 12. And as discharge continues at, let's say, the next second, time is equals to 1, what is the voltage across this capacitor? At time is equals to 30, what is the voltage across this capacitor? At time is equals to 1 minute, what is the voltage across this capacitor? That's what I want to find out. So I want to find out how voltage varies with time, how current varies with time, and the last thing I want to find out is what is the last thing? Voltage, current, charge. How charge varies with time. Got it? These are the three things I want to look for. So at a specific time after discharge started, at time is equals to 0, what is the voltage, current, and charge? Good. So where do we start? The first equation I want to get to is this one. What is the charge on the plate at any given time after discharge has started? Okay. So this is the equation I want to come to first. And for that, I start off here. Okay. Take a look. The first thing we will do is we know that current can be explained as a negative gradient of time, derivative of. What does that mean? dq by dt means rate of flow of charge flows per unit time. Okay. So in every given instantaneous time, how much charge is flowing out or in. And why is it negative over here? Why? Because dq by dt basically denotes electron flow. And my conventional current is in the opposite direction. So that's why the negative sign. If electrons are flowing in this direction, conventional current is in this direction. Do you guys remember that? That's a very common thing in electricity. Because this is the real current, because electrons flow. So if electron is moving in this direction, real current direction, conventional current, which considers the direction of positive current flow, is at the opposite direction. Got it? And so dq by dt is electron flow. Why the negative sign? Because we're considering conventional current path. Good. So I is minus dq by dt. Next. I can also express I as v by r. Well, typical v is equal to IR. Nothing to be confused about. So I. Let's equate both. Let us equate both the equation of I. So I get minus dq by dt divided by r. Shocked? Shouldn't be, because I haven't done anything crazy right now. Well, it does say my internet connection is unstable, but what to do? Mm. Okay. Anyways, so we got until this. This we figured out, right? That minus dq by dt is v by r. Now what do we do? We're basically going to change this. So did anyone say something? No. Okay. Okay, I'll just continue. Now, if this is the equation that I have ultimately when I'm joining both of these equations, what do we do next? We're basically going to move the negative sign to the other side and take this dt on the other side as well. Okay. And I'm going to bring charge on this side. And how do we do that? Before that, we have done a substitution that is from this equation. V is equals to Q by C. And this you pretty much know from the capacitance chapter. So if you are okay with V is equals to Q by C, I'll do the substitution and do the movement of variables. So V is equals to Q by C. I'll plug it in. Minus dQ by dt is equals to Q by C divided by R. Negative reciprocal. And reciprocal is equals to Q by RC. Till this be okay. And now I will do the swap of dt and Q. Okay. Till this be okay. I've just subbed in V is equals to Q by C because that is how capacitance formula works. If you're confused about that, C is equals to Q by V. Charge held on one plate per unit voltage. Don't forget that. Very important. That's pretty much the principle of the capacitance chapter. Nonetheless, you have this equation after substitution. Now I'll do a bit of swapping. Okay. I will take dq by q and dt by rc. And I'll take the negative sign on the other side. I've done this much. Fair? Fair? Good. Now, what you guys need to understand at this very important point is we have come to an important conclusion. That is, if I take this and read like this, dq by dt, dq by q is equals to minus 1 RC. Basically, the numerator is 1 times dt, right? So 1 by RC times dt. What you have over here is this value that you see, 1 by RC. This is actually a constant. What is this? A constant. This is not a variable. Does the resistance in the circuit vary? Nope. How will it? We have a fixed resistor increase, which is independent of the circuit or capacitor. And we have a capacitor with a fixed capacitance, regardless of how you set it up. I mean, if you include multiple capacitors, that's a different thing. But the capacitance of the entire circuit doesn't change. Okay? Capacitance of the entire circuit does not change. So this entire value is a constant. And you know what this constant is called? You'll get to see it later on. Okay. So this entire thing, which is going to be very, 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 very important, is a very important constant, which will explain how discharge happens for different capacitors. So let's move on. Till now, what we have understood is when we have basically put two equations of current equal to each other, we've established a general equation over here. And then what did we do? We substituted capacitance equation. Okay. And then we have an equation where I have the derivative of charge is equals to 1 by RC times dt, small change in time. Okay. This is where we are right now. A bit of complications done, but more left. Now we are at a position where we can take an integral on either side. This point onwards, things are not really in your syllabus. Okay. This integration and XYZ are not exactly in your syllabus. You don't have to worry about this. Even the few steps before it, it's not exactly in your syllabus. So you don't need to worry about it. Okay. So I'm just showing it to show how the derivation really works because some people are interested in it. And in case you understand how the equation really works from the derivation, then it will be helpful. Nonetheless, what we do over here is if you're familiar with all of this calculus from pure math, you'll understand what's going on. We basically take an integration on either side with respect to the small change that we have. On the right-hand side, we have dq. On the left-hand side, I have dt. So I take an integral on either side with respect to q on the left-hand side and with respect to time on the right-hand side. Okay. And can we do this? Is this mathematically ethical? Yes, it is. We can do this. We can definitely do this. It's not wrong. and it's not a problem. What we have basically done, we have introduced an integral on either side of the equation. Okay, and we're going to integrate both sides about same two position. What same two position? Initial point is going to be starting point. The starting point. So what is the charge when time is equals to 0, and what is the time when time starts? That is, time is equal to 0. So initial point for charge is Q naught, or maximum charge, and initial point for time is 0 because time starts at 0. We can consider here. And what is the final point? Final point for charge is going to be simply Q, because we want to find out whatever charge is at a given time. So final point for time will also be T. So what this basically means is my final charge is a variable Q, which we will plug in or find out. And my final time T is a variable T. So I find, let's say if I put in T into the equation, this T into the equation. So if let's say I put in time 2 into the equation, it will give me out the charge at that given time. That's why our final position, or the final point is a variable Q and a variable T. Okay, so that's why lower limit is Q naught and time is 0. Upper limit is Q and time T. Got it? So now we do the integration. So over here, what is the integration of 1 by Q? It is going to be ln Q. It's from pure maths. Can't help you there right now. Okay, and what is the integration of 1? Because this is a constant, I took it out of the integral. Okay, and the integration with respect to time of 1 is T. So T over here. And now I have limits, so I introduce the values into the equation. So ln Q, upper limit is Q, minus ln of Q naught. That's great. And on the right hand side, I have minus 1 by RC times the final value is T. Initial value is 0, so T minus 0. That's good. Again, I apply the log rule over here. That is, again, this is from pure math, can't help you there. I mean, just believe me that this is how things work. And here what's going to happen is I can take Q by Q naught and say both are identical. This is what I'm using. Ln Q by Q naught. Okay. This is the identity I'm using. Fair? Great. So granted, this applies. I finally have ln by Q by Q naught is equals to minus T by RC, because this is T and it gets multiplied over here. Okay, good. So now ultimately what I have is I will take this ln. And what is ln essentially? Ln essentially is log base E, whatever the function inside I have, expression I have, Q by Q naught. So I will take this E to the other side, or raise either side to the power of E, and will cancel the logarithm out on the left hand side. So basically, since I have a ln on over here, I'm going to raise both sides to the power of E, cancels the ln out over here, and it will raise this expression to the power of E. So hence I have Q by Q naught is equals to E to the power of minus T by RC. Okay. I'm not sure if you guys can hear me, but in case you can hear me and have any question, let me know. Till now, these are a bit complicated stuff that we have done. And even if you don't understand the entirety of it, glad you have an exam very soon. It's all right. You just need to be able to use the equation. But if you have any question, do let me know right now or later. So basically what I have right now is I make Q the subject, take Q naught to the other side, and I'm left with Q naught times E to the power of minus T by RC. What does this mean? That my Q at any given time is dependent on initial charge, maximum charge, times e to the power of minus t by RC. Okay. So as time increases, what do you think happens to my charge? Decreases. Because this is basically 1 by e to the power t by RC. Okay. This is what's happening. Good. Good. So granted that's what's happening, I move on and derive other forms of discharge equation. Do you understand this? That as time proceeds, my charge varies in this relationship. Time increases, charge decreases as a part of E. Okay. Now, we also want to find out how voltage varies with time and how current varies with time. We're going to do a bit of a similar thing. Let's do it. Let's do it. Deriving other forms of charge discharge equation. Now, what is Q a function of? Time, right? What do I mean by that? I is equals to Q by rate of flow of charge. If I want to find out the charge, simply multiply current times time. So when I multiply the current times how long the charge has been flowing for, I find out the total amount of charge. So if every second I have 5 coulomb of charge flowing, in 10 seconds I have 50 coulomb of charge that have flown through. Fair? So to find the charge, current times time. Good. So granted I know that. Let's do something. Remember this position of our equation? No, because this is technically new position. We did come to something similar to this. I'll show that to you. Dq by dt over here, and then we substituted this, and we got this. Okay, so we did come to a very similar case. D minus dq by dt is equals to q by rc. But what's different in our new case is we took the same equation that we have that we found out in the last step over here. We took the same equation and substituted the expression of q. What did we do? We basically differentiated on either side. Okay, we didn't basically we didn't substitute q with anything as of now, but you will see what happens. What we really did is I took a derivative of the charge with respect to time, and I took a derivative on the other side as well. But since the q naught value is not exactly a variable and it's a constant, ultimately, when you take a time derivative on the right hand side over here, what happens? Where is time over here? There, right? And if you remember from differentiation in pure math, e to the power minus x, what is the derivative of this with respect to x? Minus e to the power minus x. Okay. Similarly, when I'm taking a time derivative over here, what happens? The negative sign over here comes in front. That is it. That is it. And this is where the substitution comes in, because I know my current is equals to change in charge by change in time, q by t, technically. So if that's the case, you can say dq by dt, change in charge by change in time as well. If that's the case, can I not substitute dq by dt as I? Yes, I can. Yes, I can. dq by dt turns into current, because rate of flow of charge. Now, what we mentioned over here up says that charge ultimately is a function of time. That is why when we take a time derivative of this, right, we get current. Okay, when we take a time derivative of charge, we get current. But when we have a constant of charge, that is, where is it? That is over here, it doesn't apply because this is not a variable. This is a constant value. Let's say 50 coulomb of charge. That's a constant value. So that doesn't apply over here. Okay, so it's a constant value, which is why we don't take a time. If you take a time derivative, nothing really happens. So when we take a time derivative on the right hand side, what really happens is you have a variable t over here, and whatever sign you have in front of it or value in front of it drops down. Typical differentiation of exponential values. That's how it works. Okay. So now I is equals to what? Minus q naught by RC times e to the power minus t by RC. This is the expression for current, how current varies in a circuit with capacitor as time proceeds. Fair? A bit complicated, I would say, but not bad. Good. Good. Now, ultimately, you can also clear the equation out a bit more, okay, where you can substitute this entire expression with I naught. And for this to work, you need to understand what I naught really is. So what is I naught? Look at the right hand side. Do you know what capacitance is expressed as? Q by V. Can I substitute V is equals to IR over here? Yes, I can. Let's do that. So C is equals to Q by IR. Fair. I make current the subject. I have Q by RC. Already looks very similar. And when time is 0, my charge is Q naught. So for initial current, what will I have? Initial charge. So if I want to find initial current, I plug in initial charge, which is Q naught, divided by RC. Okay. So ultimately, what did I do? I said I naught will be equal to Q naught by RC. How did this work? Or how does this work? All I basically did is I said I substituted these two together and I found out I is equals to I varies as charge by RC. And I want to find out the final current, or not the final current, the initial current, the max current, and that will only be given to me by the initial maximum charge. So I naught, the initial maximum current, is equals to maximum charge divided by RC. Simple. So I naught is expressed as this, which is exactly what you have right over here. Okay. So that is how you have I is equals to I naught e to the power minus t by RC. Okay. Oh, and the negative sign goes away because of the same reason. That is, real current flows opposite to the conventional current. It doesn't really matter with the negative sign, but regardless, the why no negative sign in the final equation? Because real current flows opposite to conventional current. And if this is giving you the conventional current value of current, then there's no negative ultimately. Nope. We won't cover alternating current. We will start magnetic fields though. Okay. Could you hear the first part of the class, or was it not audible? Oh, okay. Fair. So ultimately, what did I get to? Two equations. One is I is equals to Q naught. Sorry, I is equals to I naught times e to the power minus t by RC. This is one of the equation where I find out current with respect to preceding time. Now, the other equation that I have is Q is equals to Q naught e to the power minus T by RC. And this tells me how charge varies with preceding time. Last one, I want to find out how voltage varies with preceding time. Simple thing I'll do for this one, this is the easier derivation, that Q is equals to Q naught e to the power minus T by RC. This is the equation I figured out first. What I'll do is divide both sides with C. Okay. Once I do that, I will have voltage is equals to V naught. Why is this V naught? C is equals to Q by V, right? So when you have maximum volt, you have maximum capacitance. Okay. Okay. Why? Because when you increase the voltage, the amount of charge that you can hold is absolutely maximum. Okay, so charge is maximum, voltage is maximum. Voltage is maximum, hence charge that you can hold on the plate is maximum. So capacitance is maximum. So basically what you plug in over here is Q naught by C gives me the maximum voltage. Okay, because when you have the maximum amount of charge, what does that mean? The voltage across is maximum, right? Right? Because we saw initially how charge and voltage varies. If I give you a bit of glimpse again. When charge is maximum, voltage is also maximum, right? Yeah, good. So the same logic I apply over here as well. When my charge is maximum, voltage is maximum. Okay, so max charge by C gives me max voltage. Done deal. So ultimately, I have again how voltage varies with preceding time. I take the maximum initial voltage. Technically, this is initial volt. This. So V naught, the naught means initial value. So this is how voltage varies with respect to time. Three equations, the star equations that you have, that's important rather than the derivation. Derivation, you maybe good to know, but otherwise, remember the equation. Now, question comes: what is time constant? I was talking to you about 1 by RC. How this is a very important constant. Okay. And why is this a very important constant? Because of RC. And I'll explain it to you right now why RC is such an interesting value or product that tells us so much about the discharge process. And I'll explain all of that step by step with mostly with example how it really works. But right now, believe me, and just understand that tau, this is called tau. This is called what? Tau. Tau is equals to RC, or time constant is equals to R times C. So when you have a larger resistance, tau is large. When you have a larger capacitance, tau is large. What is tau? What is this? It essentially means, or it is simply a measure of how long it takes for a capacitor to discharge. When tau is large, that basically means longer time is needed for complete discharge of a capacitor. And think about it logically. I have a capacitor connected to a resistor, right? There's some sort of a power supply. Or let's say it's just discharging. This capacitor had 12 volt, fully charged, and now it's discharging. When the resistor over here has a high resistance, means more obstruction for the charge. So less charge will flow per unit time. So if I have some amount of charge over here, the amount of time that it will take to discharge is much larger. That's why as R increases, tau increases, or time of discharge increases. By the way, time tau over here doesn't mean how long it takes for the full charge to discharge or the full capacitor to discharge. No, I'll explain what it means. Don't consider tau as the total amount of time needed for any capacitor to discharge. That is not the definition. I'll explain what it means. But basically, tau increases with increase in resistance or amount of time needed for discharge. What amount of discharge? I'll explain later. Wait. Another thing is, if you have a larger capacitance, that is, you get to hold more charge in your capacitor. And that also means discharge will be slow because you have more charge to discharge. Simple logic. Same resistor with an increased capacitance of the capacitor means more charge has been held in the capacitor, hence it will take more time for the capacitor to discharge. Simple. Okay, more time. Now tau, what is this? Let's understand. And this is where a lot of people get confused, and this is visible. I mean, all of these people get confused. It doesn't matter because these don't come as much. I mean, never. And this is extra. But this you get confused about is the problem because this comes in your paper. Okay. So what is this? What is tau? Time constant, tau, is basically the time taken for the charge of a capacitor to decrease to 37% or 0.37 times its initial value or its original value. So what does that mean? If I have a capacitor with 12 volt, how long does it take? Let's say it holds 50 coulomb of charge. How long does this capacitor take to reach 0.37 times 50 or 37% of its initial value? Let's all do the calculation ourselves. So 0.37 times 50, 18.5. How long does it take for the capacitor to have a charge of 18.5 or discharge to a total charge of 18.5 over here? How long does this take? That is tau. That is the time constant. That is what? The time constant. So by finding out how long it takes for a capacitor to reach 37% of its initial value, I get to understand, or I create a standardized system to understand how fast or slow a capacitor discharges. Why 37? I'll explain that as well. Don't worry. But first of all, what you need to understand with a better example is how this works. Let's say every capacitor has a built-in different value of tau, time constant. So different capacitor will mean it discharges differently. So it takes different amount of time to reach to 0.37 of its initial value or 37% of its initial value. A high capacitor will take longer time to reach 37% of its initial value. So let's say I have a 5 farad of capacitor and I have a resistance worth 2 ohms, okay, in the circuit. So this has a 50 coulomb of charge, let's say, on the plate initially, Q naught, and capacitance 5 farad and resistance is 2. What is time constant? Time constant is 10 seconds. So within the 10 seconds, it will reach 37% of its initial value. So initially, if it has 50 coulombs, what happens after, what happens after 10 seconds? It will reach 37% of its initial value, which is 18.5. So since time constant is 10, it takes 10 seconds to reach 18.5. Okay. Okay. Now from 18.5, again, how long it takes to reach 37.5% of 18.5? That is 0.37 times 18.5, that is 6.84, 6.85. It takes another 10 seconds. Another what? 10 seconds. And so on and so forth. So do you guys know what this is similar to? It is almost similar to how half-life works for decay. You haven't studied that probably. Bad example. But half-life remains constant in certain decays. Not certain, I mean, let's say radioactive decay. And half-life there remains constant. Okay. It's similar to that. It's not half-life. Don't take me wrong. This is not half-life. Nope. This is 37.5% of its life. Not half-life. Don't take me wrong. Does this look half anyhow? 50, half of 50 is 25, not 18.5. This is not half-life. Don't take me wrong. Don't get confused. This is 37.5% of its life. Why is it 37.5%? Because this is the percentage that, when figured out, has a repeating lifespan. What does that mean? It takes 10 seconds to reach 37.5% of its initial value to 18.5. It takes another 10 seconds to reach 37.5% of its initial value, 18.5. And this continues forever. This life, this period of time to reach that certain percentage stays constant. And it only works with 37.5%. No other percentage. No other. And even for this, I have pretty decent explanation, which I have not included because it will be way too much extra. So, but that's a very interesting thing as well, which I enjoy. And is will sort of paint a picture how we come to 37.5. Okay. But point is, it is such a percentage of its initial life or value that it remains, the time it took to get to that value keeps repeating on and on. So if it takes 10 seconds to go from 50 to 37.5% of its initial value, it will also take 10 seconds for the next 37.5%. Okay, so it repeats. If it was, let's say, 50%, it won't be, let's say, the same repeating time value. So if it's, let's say, 50, and then to go 25, let's say it will take 10 seconds, then 25 to, let's say, 12.5, it will take a different amount of time. Let's say, I don't know, 13 seconds, let's say. Just keep painting a picture over here. So time needed changes in that case when we are taking, let's say, half-life. So every half-life value requires a different amount of time. Over here, it is only because it's 37% that we can do this. That time constant is actually a constant. Every time you go to 37.5 of the initial value, it takes 10 seconds. That's why this is such a beautiful figure or constant, because it works. It always works. So anytime you know the time constant, you know how long it takes to reach 37.5% of its initial value. When the time constant is large, that means longer time of discharge. When the time constant is low, longer time of discharge. Sorry, less time of discharge. What did I say? So if your tau is less, lower time of discharge. Okay. If your tau is high, longer time of discharge. That's it. Simple logic. Works. Works. And that is pretty much the story of time constant, which we just covered. And you will have this come in your paper quite often. Okay. Wait, give me a moment. Good. So any question to this point? of time constant or capacitor, because next time I'm going to move on to the next chapter. Any question to this point? Time constant or capacitors? Okay, I'll take that as a no. And next thing, pretty much. By the way, now you guys should be able to solve this question. Try this. No? Do try this. Okay, that's done. Next, we want to look at magnetic fields. Okay. This is really long. Actually, it won't be done in one class. Not long. But we'll see how much we can put into one class. Yeah, 15 minutes. Give me a second. Yeah. Okay. Good. You guys ready to go get into magnetic fields? Okay. Magnetic fields, you guys have sort of worked with this topic in some depth in your GCSEs, a little bit. And this is way more in depth right now, of course, and can get very confusing if you can't visualize things. The number one thing I need from you guys is to be able to visualize whatever setup I'm giving to you. So be able to think in 3D what's going on. That's the number one thing. The problem where most students I see struggle with magnetic fields is they can't imagine what the fields look like, how the forces are acting, and half the time just goes into figuring out how things are set up. The number one skill I want from you guys, be able to figure out what's going on. Okay, good. Magnetic fields, one by one. I'll cover the definition. What is the definition of magnetic field? It is a force field in which a magnet, a current carrying conductor, or a moving charge experiences a force. What does this mean? If let's say I have a magnet, and of course, I mean permanent magnet, I mean, and of course it will have its magnetic field. So can you see this on the left hand side? So let's say this. And near this, if I bring a magnet, will it feel a force? Yes, sir. If I bring in a wire carrying current, so let's say a live wire, will it feel a force in any direction? Yes, 100%. Because the charges inside the conductor is moving, the electrons are moving. What if I bring in simply a random moving charge? So not a conductor or anything, but I'm just shooting a charge. You'll see this in spectrometers and all that. Even in this chapter, I will cover it. So will you see the charge feeling a force? Will it feel a force in any direction? Yes, it will. Okay, so the moving charge will feel a force. So magnetic field is simply defined as a place, an area, a force field, where a magnet feels a force if there is a current carrying conductor or wire as such as that feels a force, not just a wire, but a current carrying wire. And a moving charge will face a force. Three situations. And that's how I define magnetic field. Simple. What are the properties of magnetic field lines? Let's see. What you will have when you have a typical bar magnet, field lines go from the north to south, always. Now you guys probably know how to draw field lines, but always outward and curved. This one can be straight over here, outward and straight, perpendicular to over here, perpendicular over here, and outward. So one can be straight like that. Others bends towards, South Pole, like that. Okay. So that's what's happening. You have field lines from the North Pole going to the South Pole for a typical bar magnet. Good. And on the south, you have field lines coming in. Okay. It's a line out of the North Pole into the South Pole. If I have N S, another bar magnet over here, what happens? What happens? Field lines will be inward, sorry, towards the South Pole. Okay. Okay. So it will also go from, the north to south in both directions. So it will attract this and it will also attract this. Field lines never really cross each other, but basically what you will have in 3D is field lines going both to the north, sorry, both to the south on the other magnet and to the south of its own magnet, usually. So you can see a lot of 3D simulations of this. There are some very interesting ones. But basically, when you have multiple setup of magnets, field lines are somewhat uh, different than a typical bar magnet field line, which is very simple as you can see in the screen. But we have multiple magnets set up. The field lines can be a bit different. Okay, so nothing to worry about over there. Even if they give you multiple magnet setups, you should be able to draw the field lines. The thing to remember: North Pole to South Pole always. Okay, if you understand that, nothing can really go wrong. Now, the direction of a line shows the direction of force felt by a magnetic North Pole. When we were drawing electric field charges, sorry, electric field force and electric potential, okay, what did we consider as the test charge? A positive test charge. So how do you draw the field lines of a positive charge? I bring in a positive charge, test positive charge. How does it feel a force? Repulsive, outward. So field lines are outward, outward, outward. What happens for a negative charge? Sorry, negative. I bring in a test positive charge. Force is felt inward, inward, or attracted, attracted, attracted. So field lines are inward. Good. So we take the standard as the positive charge, test positive charge, 1 coulomb. Similarly, over here, what we take the standard as what force is felt by a magnetic North Pole. Think about it. If I keep a North Pole over here, it gets repelled by the North Pole, attracted by the South Pole. If I keep it here, repelled by the North Pole, attracted by the South Pole. If I keep it here, repelled by the North Pole, attracted by the South Pole. Repelled by the North Pole, attracted by the South Pole. Keep it here, attracted by the South Pole. Are you getting the remote idea I'm trying to express over here?
Sir, could you explain one more time?
Okay. So did you get the electric field part? That how we use positive charges to determine the field lines of a positive or negative charge? That you understand?
Yes.
Yes. So it's similar logic over here. What we consider as the test charge or the test magnet is what happens if I have a North Pole. I have a North Pole over here. What happens? Repulsive forces. So it gets pushed by this side, attracted to this side by the South Pole. Opposites attract. I keep it here, repelled by the North Pole, attracted by the South Pole. Okay, so it takes a path such as this. So the dotted line shows you the path taken by a typical North Pole positioned in any given position. So if it's positioned here, it takes this path. If it's
Is the
positioned here,
path taken by a positive test charge? Like if this was a
if this was a electric field thing, yeah. But since it's a magnet thing, we talk with respect to a North Pole. What is the path taken by a North Pole? Okay. Sorry, I didn't hear you.
yeah.
Okay, perfect. So ultimately, what we are doing is these field lines express how or what path is taken by a North Pole if positioned there. Okay. So the arrows show you the direction of force, and the field lines show you the path taken by the North Pole. Okay, clear? So these two. Any other question?
No.
Okay, perfect. So when lines are closer, field lines are stronger. This logic applies as usual. You have electric field, gravitational field, or magnetic fields. These are the three fields you're working with in your A levels: magnetic, electric, and gravitational. So when you have field lines closer here, the force felt larger. By what? Let's say a North Pole. So repulsive force, if I have a North Pole over here, is way large. Higher density of field line. Same over here. If I have a North Pole there, higher density of field line. So what happens? The force felt larger. What happens if I have a North Pole here? Well, field lines are more far apart, so the net force felt by the North Pole is less. Okay, fair, done. Um, the lines never cross each other. I just mentioned it. You will never anywhere, not specific to magnetic fields. Any field line, you can't have field lines that cross each other. So you can't have this field line crossing this field line. So you can't have this intersection ever, ever. Okay. So field lines never cross each other or intersect each other. Uh, they're basically going to weave its own path. Okay, good. So the lines never cross each other. That's typical to all fields. And field lines are continuous, meaning there are no breaks in the line. What that really means is it doesn't have breaks in line in the sense you usually when you're drawing the line, it should be solid line. Okay, so I'm just showing it over here. But more than that, what it really means is regardless of where I position the force, sorry, where I position the North Pole, okay, it will always feel a certain amount of force. Okay, you'll always feel a certain amount of force. It is not that at any position the force breaks off. I mean, the force felt at every position is different. Here it's different, here it's different, here it's different. Even though it's the same path, doesn't matter. This is one path, but force changes as you travel. But it's a continuous path where force is constantly felt. Force will never be zero over here, really. So it's a continuous act of force on the magnet, on the field line. Okay, that is the point. How can we create magnetic fields? We somewhat discussed this. We can move electric charge in conductors, that is in a wire, and keep that wire in a magnetic field. You will see this thing quite commonly. Let's say, whoops, North Pole. Okay, and so this is South Pole. Okay, so north to south, this is how the field lines will look like. Parallel field lines. And let's say I have a wire right through carrying conventional current in this direction. So now this wire will feel a force. Why? Because there are electrons. Oops. There are electrons moving in this conductor. Okay. Moving forward, let's say. Not moving forward. If conventional current is in this direction, forward, electrons are moving in this direction, backward. Conventional current is opposite to the direction of real current. Always remember that. So real current is flowing backward, but conventional current is forward, let's say. Yeah.
So, you mean electrons is flowing backwards? Right?
Yes, 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 yes. Positive charge you could say is flowing forward based on conventional current, but yeah, and positive charge as in protons don't move. It's just electron flowing. So yeah, electrons are flowing in this direction, and we say conventional current is forward. Okay,
Yeah.
perfect. So in this case, when charges are moving inside the wire, what do we have? We have a force. And what is that force? I mean, downward or upward, you will see later. Point is, it does feel a force, either upward or downward. And what you will see in a lot of videos in Reels, YouTube, or somewhere is this wire will bend upward or downward depending on Fleming's left-hand rule. And I'll show that to you or teach that to you today. So the wire bends. Why? Because the force is acting on it. Okay, because the force is acting on it. So point is, a current carrying conductor feels a force. And if it's not a current carrying conductor, if we have a permanent magnet, even then, the magnet, of course, feels a force. That goes without saying. If you bring in two magnets, obviously there's repulsion or attraction there. Other thing, when you have, what is it? Same thing. You have a magnetic field. I have a charge, let's say, electron. It's not moving, it's static. This will not feel a force until and unless charges move. They don't feel a force by magnetic fields. Get it? So if charges are not moving, they don't feel a force by the magnetic field. If charges are static in one place, so I have a piece of charge over there where E is, it won't feel a force. Charges need to move to feel a force. Very important fundamental. Keep that clear in your head. And magnetic field line is also known as B field. You will keep seeing this again and again and again. B field means magnetic field. Good. Good. Next. The first thing that I want to clarify is the notations that we are going to use. One very important notation is the circle and dot. Do you understand what magnetic fields mean? It is basically the direction from north to south. Force field from north to south. So the path taken by a north pole if positioned on that line. Okay, typical field lines. Okay, so we know what field lines mean. Good. So that is what a field line is, and that field line or the field direction I can denote by a cross or a dot. What does that mean? If I have a cross, the magnetic field is into the page. Now, you can have a setup where they say, I have magnets like this, north, and I have south, like this, and it's the field lines are like rightwards. That's okay. If this is the field they're giving, fair enough, no problem. And then let's say they say current is in this direction and force felt would be downwards. This is easy to understand, no problem. But life isn't this easy. You will often have cases where they say, I'm trying to create the situation. Current is in this direction, and they say force felt on this is upwards. What is the direction of field, magnetic field? So the force is upwards as in towards the top of the page. So like the wire bends like this. So force felt is upwards. Force, this is current. What is the direction of magnetic field? It will either be into the page or outward of the page. So we say if the magnetic field, in this case, it's going to be like current is here, force is upwards, so magnetic field will be into the page. So I'll explain when it's into the page and outside and how we figure it out using Fleming's rule, left-hand rule. That's fine. Don't worry about that. But what I'm clarifying right now is the notation. So when you have circle cross means into the page. So magnetic field is into the page. So this is to make our lives easier when we're working with 3D stuffs and we can't really draw great 3D images. So it's incapability of human beings turning into symbols. Okay. So when you have this dot circle cross, it's into the page. Magnetic field is into the page. To paint a picture for you guys, I'll do this for the sake of Now, okay, you know what? I can't do that right now. What I was going to do is show you live how this really works, but for now, just understand that what into the page really means. So this is the force and current is on the same plane. Okay, so one is upwards, the other is rightwards. Hmm. And the X denotes into the page, so on a different plane. So let's say consider this the Z axis. If Y and X is on the same plane, it's a 2D plane. The Z axis is in a different plane. It is normal to the plane of Y and X, right? So typically what you have Y, X, and Z goes into perpendicular to each Y and X, right? That is how you think of it, right? So that Z is into the plane of Y and X. So if Y and X is on the plane of my paper, then Z is into the paper or inside the paper, and we denote that as X. If Z is out of the paper, like this, both perpendicular to Y and perpendicular to X, we have Z being dot dotted out of the page, we say, and it is coming out of the page. So field lines in this case is coming out of the page. So up of the top of the page is direction of force, right of the page is direction of current, let's say. I mean, in that case, current direction will change, but anyways. So out of the page is going to be magnetic field coming out of the page. So it is normal to this XY plane, 2D plane, but perpendicular to each of the components. Okay. So do you understand what normal and perpendicular means? In essence, like, I mean, we use it interchangeably. What normal really means when you have a component or any variable that is perpendicular to the plane itself. So if this is a paper, right, and this is a force out of the paper, we say this force is normal to my plane. This is the plane. And when you have two components when you have two components which are perpendicular to each other, we say, well, this is up of the paper, this is right of the paper. These two components are perpendicular to each other. Do we get the difference? Do we understand? Oh, good. So out of the page, into the page. Dot, sorry. Yeah, dot and cross. Okay. This is okay, clear? Why am I stretching this way more than I should? Because I need you guys to paint a picture in your brain whenever I work with any setup. This is the most important. People just can't imagine things when they're working with this topic, which is why this is one of the most difficult topic to teach, usually virtually. Anyways, I won't get into difficult stuff today, so it should be easy. Any question till now? Hopefully not. So first thing, we're gonna look at a setup where I have a live wire that is upwards. Can you see upwards? This is the wire, and current is moving upwards. So we're considering positive flow of conventional current. You know the right hand thumb rule? If you don't know why, we're going to cover it. But basically, let's say upward is the direction of current. I mean, it could be either way, but let's say upward is direction of current. Your hand's direction is showing the direction of field. So if upward is the direction of current, this is how the magnetic field line looks like. So it's sort of anti-clockwise. Okay, anti-clockwise like this. So this is the field line, and the field lines will the separation of the field lines increases with increasing or with successive field line. So every successive field line will have a increased separation. You will look over here. So I have drawn this top view. This is what? Top view. To make your life easier, I've always like done these, what to call this? I've taken snapshots and shown you guys what I'm visualizing so that you can understand what we're looking at. Okay. So if on a 2D paper, I've tried my best to try and make it easy to visualize. Okay. If you still get confused, let me know. So I'm taking a top view, and on the top view, I see dot. What does dot mean? Coming out or into the page? Is the current coming out of the page or into the page? Take a guess. Yeah, out of the page. Okay. So in this case, we have the current out of the page. So towards the top view. Okay. So as I'm looking at it, out of the page. Good. And these lines, these are the field lines. And as you can see, it increases, as in the separation increases with increasing or successive field line. Okay. So it just shows that force gets weaker as you move away from the wire. Okay. So the force field gets weaker as you move away from the wire. Good. Good. You'll have to draw this multiple times on your paper. Very common question. So that's the top view that you can see. Basically, it's the direction of force is, sorry, direction of field line is like this, anti-clockwise. Great. So field gets weaker as you move away. Now the side view is as in this view. So you're looking from the side of your hand. And what you see is this is the middle line. This is the middle line. And on either side, you're looking at current coming out. So current coming out and current going in. So current going in. Got it? Got it? So multiple ways to visualize the same thing. This is drawn in 3D. This is drawn in 2D. This is drawn in 2D as well. So I've drawn two aspects of it for you guys to be able to visualize it. Okay. This is not needed, but this is how B field is measured. So as you increase away from the, as in move away from the source of the magnetic field or the current, your B field or magnetic field strength decreases. Next one. This is another setup. I'm just showing you a setup, nothing else. Give me a moment. I'm drink some water. Okay. So the next one that you have is a coil, pretty much. So what happens over here? You have a positive supply, negative supply, current flows, conventional current in this direction that you can see. Red arrows, follow the red arrows, and that's a conventional current flow. Good. So over here, what happens? As the current is moving upwards, it creates, if you use your right hand grip rule, upwards is a direction of current. So field lines are somewhat like this. Okay. Okay. Good. So I'm taking the top view that is from this point. That is, I'm seeing this wire as a straight line, technically speaking. So this is this. This is the field line. Okay, this is the field line, and I can see this thing. To me, looks like a straight line over here. Okay, because I'm looking at it from the top. Try to visualize this. Okay. Good. Now, if over here current is out of the page, right? Out of the page, dot. Current is into the page, cross. And I draw the field lines. And as you move away from the source, the spacing between the field lines increase. Spacing between the field lines increase. Good. And for the dot that you have out of the page, field lines are anti-clockwise. For the cross, that is field lines into, sorry, current into the page, I have clockwise direction of field lines. This is clockwise. Good. I can also see it from the side. From the side, as you can see the arc, this is the arc, this is the arc. Okay. Okay. And as current flows, this is basically side as in from this side. You're looking at it from here, straight up. So you're looking at field lines coming out, right? Field lines coming out. Good. And field lines going in. Okay. Field lines going in. Great. Same over here. Over here, field lines are getting into the page. Okay. Getting into the page. And here, coming out of the page, coming out of the page. Great. And over here, what happens? Why have I drawn this? To paint a picture. Here, field lines are, all of them are what? Going into the page, right? So the direction, notice, is what? All in the same direction. You know what happens here? Repulsion happens. What happens? Repulsion happens. And the force is felt outwards. I'm painting basic concepts over here because we'll get into technicalities later on. Don't worry. I'm painting the concept over here. Okay. So look, ultimately what's happening here? I have field lines in the same direction, hence repulsion. Okay, great. So you, by the way, your right hand grip rule, your direction of thumb can be considered either a field line or a direction of current, whichever you wish to use. Third thing we will get over is the solenoid thing. So you've worked with solenoids in IGCSE, GCSE at some point. What do? You have iron core, you have some sort of a core that is magnetic in nature, and you wrap around like this a bunch of coils. Okay, great. So in this setup, I have current coming down. So basically it goes behind the thing and comes down. So upward here and downward here. Great. Good. So this is how the field lines look. And when I wrap around my hand, this is how the field lines look. Okay. So my arms, sorry, not arms, my fingers show the direction of magnetic field, and my fingers show the direction of current, right? My fingers over here, index, middle finger, pinky, all of them show the direction of current because these lines are the current direction, and my thumb shows the direction of magnetic field. What magnetic field? The thumb really shows the North Pole. So as in magnetic field as in going like this. Okay. So outward of the north into the south. So your thumb is showing the direction of North Pole. So whenever you consider your fingers over here to be the direction of current, your thumb points towards the North Pole. Remember that. So the finger pointing out, thumb points the North Pole. Very good. Let's take a bunch of sides, views. Right? Top view, side view. Good. I have the side view over here. This great thing. Now over here with the side view, I'm looking at it basically from the side over here, right? I'm looking at this thing, and what I can see is a bunch of wires, coil. You can see the coil, and you see the field line. So field line is over here straight, almost curved, and the field lines, if you notice the direction, is inside the magnetic material, that is inside the solenoid. It is going over here through the north and then outward to the south. Completes a cycle. So outside the coil, it goes from the north to the south. That is clear. That is all right. That is all right. But what happens inside? This cycle is obviously complete. So inside the coil, what really happens? Field lines are in this direction, south to north. Okay. Then comes out, goes to the south. Okay. Okay. Also think of it this way. When you have a magnetic material, all the North Pole, all of the how the magnet is designed is North Pole of it all is in this portion, and South Pole of it is all in this direction. So basically, the North attribute gets accumulated in this portion, South attributes accumulated in this portion. So basically, the field inside, if I have a North Pole, it's accumulating itself in this direction or towards the left portion of the solid. That's one way to think of it. It's true or not, it's a different thing, but uh, that's one way to rationalize why inside the solenoid, it's inside the metal, I have field lines going from south to north. Okay. So your thumb is pointing towards the north, right? And is showing the field line inside the magnetic material. That is great. That is good. Great. And the other thing is, I could, if I want, plot. This is not in your syllabus, not in your syllabus really. What I've written. So over here, right in the middle, over here, what you have is the greatest concentration of magnetic field. So what you're looking at technically is how magnetic field strength varies when the magnetic field lines are closest together, and how when the magnetic field lines separate or widen out, how the magnetic field strength changes. So this position length is half. The field lines are most uniform and closest together. So your field strength over there is maximum. But this is not needed. Not needed. You don't need to see this really. Okay. Great. So the other way to look at it, we looked at the side view. So from here, that's good. We can also look at it from the top view, from that direction. What do we have over there? What do we have it? We have looking at field lines going here, 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 because we're looking at it from the top. So we're seeing like this going upwards, technically. Got it? Could I paint a picture? That's pretty much the entire point of doing all this shenanigan. Okay. So now I see over here my current direction appointed as dot because it's going down or into the page. So current is going down or into the page from my view. From my view, it's going away from my view to the page. And from here, if I have my eye over here, it's coming out of the page or coming towards my eyeball. So cross. Got it? So this is my top view. The point of doing all this is to give you guys the exercise of visualizing things. Okay. Good. Last thing that I will show you guys an end for today. I don't want to get into heavy stuff with magnetic field. Next class onwards, you have to be coming with a bit more of a ask question type thing because things are going to get a bit way more complicated. You're going to look at Hall probes. That's pretty much the last thing, but particle velocities, force and charge particles, field line stuffs. These are very complicated stuff usually. So you guys need to be able to comprehend things, sit down, ask, and sort it out. Okay, last thing, Helmholtz coil doesn't come as frequently, but still showing you the setup. You have the coils over here. The green lines show the current, and the red lines are showing the field lines around it. So, you know what? I'll change the color of the field. There. Okay. So what do you have ultimately? You have the coil, which shows the direction of current. Coil over here, direction of current, and you have field lines coming in, right, and going out. So when you use your grip, grip. When you grip around the coil, that is, this is your finger and your thumb points in this direction. So this direction points North Pole, and rightfully so, because field lines over here are going out of the north and into the south. This is south. So your thumb points towards the north direction. So in this setup, you get the North Pole, you get the South Pole over here. You got it? All good? All good? So this is the Helmholtz coil that you typically have. And around this again, around this coil that you have, this wire itself has its own magnetic field, of course. So if my current is going downwards, right? Here also downwards. So the magnetic field around this coil is going in like this, and then coming out backwards. So that is why you have the field lines like this. So it's a bunch of these small magnetic field line that you have like this, and then from the backward, it is coming out like this. So from the backwards direction, it is coming out like this. So field is inward. Okay, try to imagine this, try to draw this, try to see how it works for you with your right-hand grip rule. This is how it works. So from the top view, as looking down on basically this entire circle looks like a piece of length over here, right? Because I'm looking from the top view, right? So just basically whatever the diameter is, I'm just seeing this as the diameter D. Okay, so I'm looking from the top. So over here, what I have is current moving up. So out of the page, this portion out of the page, and then coming out, going into FS cross. Same with the other coil, coming out, going in. And when I draw the field line out of this, I have the, if you use a right hand grip rule, thumb is pointing into the page and your rest of the fingers are pointing around, right? Great. And this one, thumb pointing out of the page, field lines going around in this direction. So what you see is ultimately the field lines point in this, you'll see a bit of wobble over here. That is mostly due to the fact of multiple uh, conducting wires and having their own magnetic field. And when you have multiple magnetic fields joined together, the magnetic fields will act a bit differently. Remember, I was showing you guys uh, over here, I was telling you guys multiple magnets may be set up and their field lines will look a bit different. I was telling this towards the beginning of this chapter. And the reason I was saying that is multiple magnets, when acting together, will have joint fields. So their field lines will join together. And when they do that, they act a bit different or unique. So over here, what you have, when you're joining the field lines individually, so this kind conductor going into the page, coming out of the page, has field lines like this, circular. And as you join them together, basically, if this is going in this direction, oops, if this is going clockwise, like that, no, anti-clockwise, and this is also going anti-clockwise, I basically join their field lines like this. Okay, what did I erase? Okay. So I basically join their field lines like this. Okay, that's why over here you have a bit of a bend. Okay, because over here you see a space between the field lines, right? This is why this warps around. So the field lines come in, the warp around. It's not important. It's not that important. Not to worry about it. Warps around over here and then goes in. So I basically joined the field line. So ultimately, it looks something like this. Okay. Okay. Somewhat like this. That's why you have a bit of bend over here. No problem. Now, same with over here, going into the beach. I have clockwise magnetic field. So basically, this is the downward field over here. I mean, downward current over here. Downward current. Okay, so into the beach. So all you're doing is mapping your right hand grip in the direction of current and finding the field out. Got it? And when you join the fields together, you get the net direction of where the north is. This is where the north is, this is where the south is. Because it goes and comes to the north, the magnetic field line, I mean. So it goes from the north to the south. So if you join all the magnetic field lines, this is how they join up. So this is why this is north. Okay. So all of this action that I do with 1, 2, 3, 4 examples, finding what the orientation is, how it looks in 3D, how I'm painting the field lines, how I'm finding out the current direction, how I'm finding north and south, all of these are important. This is the fundamental of what we're going to do later on. Everything we're going to do, which is going to get pretty complicated, is built on this fundamental. Understanding north-south poles, understanding right-hand grip rule, understanding Fleming's left-hand rule, which I will cover next class. But all of these things very important. Okay. And on that note, I'll end for today's class. Internet been pretty bad, but hopefully you can see the recording, rewatch the entire thing, and no lag in the recording, hopefully. Okay. So any question for today's class? We touched upon magnetic fields. Next class we'll complete 2/3 of magnetic field and still will be left with a decent bit. Might take a bit long, but let's see how fast we can finish it. But yeah, all okay, all good. Any other question for today's class? No, I'll give you guys a recording link. Wait, give me a moment. Today is whatever today is, Sunday. I pasted the link in. Okay, this is where I'll upload today's class. So if you have blacked out, not being able to hear, no problem. It will be available over here. Okay, so I'll end the class with that. Yeah.
Sir, will you upload the link in Google Classroom,
Yeah, sure.
or will you send it here?
I sent it over here in the chat, the link.
Sir, I can't see it. Can you send it again?
Yeah, sure. Can you see now?
Yeah.
Perfect.
Thank you.
Okay. So you can copy it. Hopefully by today I'll have it uploaded. All good. So hopefully see you guys next Friday. Okay. Friday I'll have today. These fields are very important because tough things come from this chapter. Magnetic fields can tough. They can. It's not about complicating the thing. It's more about the topic itself is pretty complicated. So next class will be on. Let me see. Yeah, it is on Friday. So see you guys on Friday, whatever the date is. And yeah, any other question, let me know. Otherwise, I'll end the class. Yeah.
Yeah, thank you, sir.
Okay, great. Bye bye.